A trigonometric function is a relation that uses sine, tangent, cosine, cosecant, cotangent, and secant that represent the ratios of the sides of a triangle. Just like the other functions, we can get the limit of trigonometric functions through graph of the function and table of values. When the function does not result to an indeterminate form, we may evaluate the function at x equals a. Let's have an example. Find the limit of sine x as x approaches 0. Note that the limit has two sides, which means that we can approach 0 from the left and from the right. Working on the left side, we choose values coming from the left of 0 and evaluating sine x. Make sure that your scientific calculator is in degree mode to get the values presented in the table. From the table of values, we can see that as x approaches 0 from the left, the value of the function gets closer to 0. Hence, the limit of sine x as x approaches 0 from the left is 0. Choosing a set of values coming from the right, we can see that as x approaches 0 from the right, the value of the function gets closer to 0. From this, we can say that the limit of sine x as x approaches 0 from the right is 0. Now, since both the sides of the limits are equal to 0, therefore conclude that the limit of sine x as x approaches 0 is 0. Confirming with the graph of sine x, we clearly see that the limit of sine x as x approaches 0 is 0. Aside from that, we can also find the limit of the given function by evaluating the function at x equals 0. So we get f of 0 equals sine 0. Using our calculator, we will get 0. Therefore, the limit of sine x as x approaches 0 is 0. Let's work on our next example. Find the limit of cosine x as x approaches pi n plus pi over 2, where n is an element of the set of integers. This time, make sure that your scientific calculator is in radian mode since we are going to use the multiples of pi as the domain of the function. Let's say we choose n as the set containing -1, 0, 1, 2. Substituting the value of n to the equation pi n plus pi over 2, we will be able to get the value of x. For example, if we have n equals -1, we will have pi times -1 plus pi over 2. When simplified, will give us negative pi over 2. Then evaluating the function f of x equals cosine x with the found values of x, we would be able to get 0, leading us to our conclusion that the limit of cosine x as x approaches pi n plus pi over 2 is 0. If we use graphing method, we can clearly see the critical points that will help us determine the limits of the given function. Notice that the ordinates of these points are all 0. Therefore, the limit of cosine x as x approaches pi n plus pi over 2, where n is an element of the set of integers, is 0. This time, let us evaluate the limit of sine x over x as x approaches 0. Notice that if we will substitute 0 to x, we will arrive at an indeterminate form, which is 0 over 0. In this case, we can use either graphing or table of values in evaluating the limits of this function. Using table of values, notice that as x approaches 0 from the left, the value of the function gets closer to 1. Hence, we can say the limit of sine x over x as x approaches 0 from the left is 1. Evaluating the right side limits, we will also see that as the value of x gets closer to 0, the value of f of x gets closer to 1. Hence, we say that the limit of sine x over x as x approaches 0 from the right is 1. Since both of the sides of the limit are equal to 1, therefore, the limit of sine x over x as x approaches 0 is 1. Let's evaluate the limit of sine x over x as x approaches 0 graphically. If we will trace the graph, we can see that as x approaches 0 from the left, we will have 1. On the other side, as x approaches 0 from the right, function gets closer to 1. Thus confirming our answer a while ago that the limit of sine x over x as x approaches 0 is 1. What about we evaluate the limit of 1 minus cosine x over x as x approaches 0? If we will use direct substitution, just like the limit of sine x over x as x approaches 0, we will arrive at an indeterminate form. In this case, let's evaluate the limit using table of values. Evaluating the left side limits of the given function, we can say that the limit of 1 minus cosine x all over x as x approaches 0 from the left is 0. Evaluating the right side limit, the limit of 1 minus cosine x all over x as x approaches 0 from the right is 0. Now, since both sides of the limits are equal to 0, we can conclude that the limit of 1 minus cosine x all over x as x approaches 0 is 0. Confirming our answer, we can see in the graph as x approaches 0 from the left, we will have 0. As x approaches 0 from the right, we will also get 0. Now let us evaluate expressions involving the limit of sine x over x as x approaches 0 and the limit of 1 minus cosine x all over x as x approaches 0. An example of such expression is sine 2x over x. Now let's evaluate the limits of sine 2x over x as x approaches 0. We rewrite this expression to the limit of 2 sine x over x as x approaches 0. Applying the limit laws on product of a constant and a function, we will have 2 times the limit of sine x over x as x approaches 0. Now take note that this expression is equal to 1. Thus we will have 2 times 1. When simplified, this will result to 2. Therefore, the limit of sine 2x over x as x approaches 0 is 2. Let's confirm with the graph of the function. As x approaches 0 from the left, we will get 2. On the other hand, as x approaches 0 from the right, we will also get 2. Thus confirming our answer that the limit of sine 2x over x as x approaches 0 is 2. Let's try also evaluating the limits of 4 minus 4 cosine x all over x as x approaches 0. Let's try evaluating the limits of 4 minus 4 cosine x all over x as x approaches 0. Since this involves the expression the limit of 1 minus cosine x all over x as x approaches 0, we have to extract that expression from the given function. Factoring out, we will have 4 times the quantity 1 minus cosine x all over x as x approaches 0. Applying the limit law of product of a constant and a function, we will have 4 times the limits of 1 minus cosine x all over x as x approaches 0. Now take note that this expression is equal to 0, thus giving us the expression 4 times 0. Simplifying this, we will have 0. Therefore, the limits of 4 minus 4 cosine x all over x as x approaches 0 is 0. Now let's confirm using the graph of the function. As x approaches 0 from the left, we will have 0. As x approaches 0 from the right, we also get 0. Thus confirming our answer that the limits of 4 minus 4 cosine x all over x as x approaches 0 is 0. Remember that we can evaluate the limits of exponential, logarithmic, and trigonometric functions by evaluating the function at x equals a. However, if you have arrived at an indeterminate form after evaluating the function at x equals a, just like evaluating algebraic functions, use graphical and tabular methods. When evaluating the limits of functions involving the expressions below, all we have to do is to factor out this expression and then substitute 1 for the limits of e raised to x minus 1 all over x as x approaches 0 and the limits of sine x over x as x approaches 0, and 0 for the limits of 1 minus cosine x all over x as x approaches 0.
Thank you for joining me in understanding the limit of transcendental functions. See you again!